And here we have a few samples of rocks from the Edwards group here in Austin, Texas. What we can see from these rocks, and I'm leaving my cell phone on top of it for scale, is the incredible variability of pore sizes, throat sizes, pore connectivity. All of these happening in a very short distance. The total porosity is relatively large, the connectivity maybe not so, throat sizes are incredibly variable, the efficiency of flow of these rock probably is not very good. But that's the kind of rocks that we see in carbonate. So we see a great variability of pore sizes, throat sizes, texture, fabric, mechanical properties, elastic properties are also variable as a consequence of these properties. And of course the question is, what instruments, what physics should one use both in the laboratory or in the borehole to be able to observe, quantify, detect all of these properties so that we can reliably assess the storage and flow properties, the mechanical properties of these rocks. And of course, the scale is very important because you can imagine that by looking at small blocks of these rocks and sending them to the laboratory, probably the measurements that come from those tests in the laboratory will not be reliable given the size of these features and the connectivity that they have, the scale of connectivity. And it's very important to also imagine the variability of these pore sizes, throat sizes, and the impact they have on scale. For instance, between wells, the scale between wells. So that's the reason why it's very important to always remember the variability of properties with respect to a dominant or important scale that one has to work with when assessing storage and flow properties. And here's a closer view of these features. It's important to navigate through all of them to see the variability. Maybe it's also possible to see the marks of living organisms or shells and to observe how they were able to have such a strong impact on the pore sizes, throat sizes, pore fabric of these rock. Very important to understand storage and flow properties of all of these features of the rock in any context. Very, very important. And here we have yet another piece of Edwards limestone with multiple features, multiple pore structures, macropores, mesopores, micropores. And what I'm going to show you is to assess the properties of these rocks indirectly without having to do flow experiments. One of the possibilities is to use magnetic resonance. Please look at the variability here of pore sizes, throat sizes. So how is magnetic resonance going to work to indicate to us this variability of throat sizes? What percent of the pore sizes are small? Let's say smaller than a few microns. What percentage of the pore sizes here are larger than 100 microns, etc. So how am I going to do that? Well, of course, there are many ways. Standard technique is to cut a plug of these rock and send it to the laboratory, and the plug will give you a pore size distribution based on magnetic resonance measurements. So how does that work? Very interestingly. So magnetic resonance is based on the principle that protons, which are the nuclei of hydrogen atoms containing water, like shown here, this is water, they behave like a magnet. They have spin. And what magnetic resonance does is to make use of that very important principle that each one of the protons that are the nuclei of hydrogen atoms behaves like a magnet. So we're going to magnetize those protons. And we're going to, when we magnetize them, we are going to generate a magnetic field with a given frequency. That's a Larmor frequency. And then we're going to spin them at a 180-degree plane, and at that point we're going to force them to do random walks in the porous medium. So the assumption is that to probe this rock with magnetic resonance, we have to make sure that the fluids included in the rock have hydrogen. This is a very, very important condition. And once we have hydrogen in the pores, then all the nuclei of hydrogen, the protons, we are going to polarize them. That's the first thing we're going to do. So you take, like in this example, in this sample of water, we have lots of hydrogen, of course, and the hydrogen is protons. And what we're going to do is to apply a magnetic field, a constant, we call it DC, space constant magnetic field, and polarize all these molecules. And then once we polarize them, then we are going to sense that the, in this case, this bottle of water we have will have an effective magnetization. Not only that, but the frequency at which this magnetic signal will happen will be a function of the so-called Larmor frequency. So I'll say more about this, but let me return to the fact that the protons that we have in hydrogen behave like a magnet. And here we have a toy, a gyroscope that I'm holding. And what is interesting about the gyroscope, of course, this works with the action of gravity, but I'm going to show you that the principles of a gyroscope are analogous to the principles of magnetization that we have in a proton. Here we have the alignment. That would be the main axis of the proton, and that's how it behaves like a magnet. Of course, it has can have a random orientation and so forth, so on, like all the molecules that we have in the water. Of course, if you were to just measure a magnetic field coming from the water bottle, the magnetic field that you will measure will be effectively zero, because all the molecules, the protons that we have in the water sample here, will be aligned in random directions. So effectively, the randomness of directionality of these magnets will cause a net zero effect. But what if I polarize all of them? What if I apply an external magnetic field that forces all the protons in this water bottle to align? That's what we do. We align them. That's the first step in magnetic resonance. We polarize them with a magnet, with a strong magnet, with a space constant magnet. And then once they're polarized, they begin to precede. You will see that, and the precession is going to be aligned according to the axis of the magnet. And this precession of the molecules is going to be at a precise frequency, which is the Larmor frequency. For hydrogen, and given the magnetic the intensity of the external magnetic field applied with the magnet, we can predict what that frequency will be. And then what happens is that these molecules will be rotating just like a gyroscope. So let me show you that. You can see the precession of this gyroscope the frequency of precession is related to the force of gravity, but here in the case of proton magnetization, the frequency of precession is dictated by the magnitude of the applied external DC magnetic field. That's what the protons do when they're polarized. They begin to precede at this very particular frequency, that is the Larmor frequency. Now we have this gyroscope. You can see has an angular momentum, is now beginning to precede because of the action of the gravity field, and that's actually the precession that we have when we apply a magnetic field to a proton. And that action is, that frequency is the one that we sense with the Larmor frequency. So it's actually very interesting to see the analogy between a gyroscope and the spin magnetization that happens with a proton. And then after we subject these protons to polarization and then transverse relaxation and then random walks, diffusion in the porous medium, then the time of magnetization decay will be an indication of pore sizes, number one, second, fluid types, and third, possible gradients in the applied external DC magnetic field. And that's how we probe this rock in the laboratory as well as in the borehole, because we have magnetic resonance measurements in the borehole. And of course, we also look at the acoustic pulses. We send an acoustic pulse through here and we measure the time of flight to the rock, and then the time of flight will be related to the porosity, that is the fluids contained, and also the solids, and to some extent the time of flight will also be influenced by the shape, connectivity of the pores. So we essentially send all kinds of physics. We shine this rock with all kinds of physics so that we have a diversity of measurements that together they can help us to understand the storage flow properties and also the geomechanical properties of this rock. So today's lecture is going to be centered about some of these properties, and we're going to look at borehole measurements, and we're going to look at ways to integrate all those measurements to get a holistic view of carbonate rocks. So stay tuned, let's go for it, and fasten your seat belts to this last part 3 of the Carbonate trilogy. Hello everybody, how are you doing today? I hope everybody's healthy, I hope everybody's safe, I hope everybody's happy, most important, and I hope everybody's very, very excited about this Carbonate trilogy. Today we're going to talk about part 3 and last of the Carbonate trilogy. And the subject that we're going to cover is advanced borehole measurements across complex carbonate rocks. What I'm going to do is, these are the objectives that I introduced before, but I want to emphasize point number 5 on this list that says introduce the use of advanced well logs that are used for the analysis of features in carbonate rocks, especially features that have to do with great spatial complexity that we have seen so far in outcrops, in rocks, everything else. So we have to be absolutely very, very careful about these features. And there are advanced well logs, we call them boutique well logs, such as magnetic resonance, borehole images, formation testers, spectroscopy, that are ideal for conditions like this. I'm going to examine those, and we're going to look at some examples. Now, let me also remind you that several of the elements of this lecture are contained in the PowerPoint presentations that we have, and also some of the examples are in the compendium, parts 1 or 2, and I'm going to use some of the Schlumberger interpretation charts. And I've been saying this, chapters 6, 7, 9, and 10, and 11 of the textbook contain very important information about the subjects that I'll be covering here today. And last but not least, I want to remind you that the last section of the binder with the compendium part 1 has several carbonate examples that I want you to look at, because I worked them out from beginning to end with all kinds of details, photographs, plots. So they're very, very good for reviewing some of this material. Now, why are we here today? Because carbonates, especially carbonate rocks that are extremely complex, like this block that I'm here, this is in Brazil. It's very close to Sao Paulo. And this block is all stromatolites in carbonates, and they produce hydrocarbon. Actually, they produce hydrocarbons in the deep water carbonate reservoir systems that they have in Brazil, Campos Basin, Santos Basin. Very, very interesting, massive developments of carbonates, and also very complex and very difficult to assess in their storage and flow properties. So what do we do with that? Well, we have to throw all kinds of information. We have all kinds of data, all kinds of possibilities, and those possibilities include conventional well logs, massive amount of core samples and measurements, borehole images, magnetic resonance logs, advanced acoustic logs, and formation tester measurements, and on occasion spectroscopy logs. Now, all of these are boutique borehole measurements, and because of that, they're expensive. So the tendency is to acquire these very expensive measurements in key wells, key exploratory wells, or key wells based on their location in the reservoir, and to use that wealth of information to calibrate, if you will, all of the properties so that that calibration, that excess of and diversity of information can be used to complement conventional well logs that will be acquired in other wells within the same reservoir. So that's the reason why we have to be careful with these measurements. We cannot, because they're so expensive, we cannot acquire them everywhere. And also please remember that the acquisition of these logs is not done across the entire well. We only acquire them across the section of the well that is of interest to us. And some of these measurements are logging while drilling measurements, and some of them are wireline measurements. I'm mostly going to be talking about wireline measurements, but please bear in mind that many of these can now be acquired in the logging while drilling mode. All right, let's go for it. So here is a section of a carbonate in the Permian Basin. And these are, it's a complex carbonate, and you can see that the dark areas of the carbonate here are all impregnated with oil. Some are not. And why so? Well, because the properties of the reservoir are changing. So when we do look at logs, such as the ones shown here, we are looking at a diversity of measurements. Resistivity, gamma ray, density, spectral gamma ray, and here we have a multitude of core measurements. Those are the points that you see here for permeability. Those are the points that you see here for porosity. But interestingly enough, this variability is already being smoothed by the volume of investigation of the log. So that's the reason why sometimes we have to acquire core data to complement the logs and to guide the estimation of properties from the logs. But in very, very complex carbonates, some of the conventional well logs that we see here are not sufficient to do the analysis. So we have to resort to other elements or other measurements. Here is a display of carbonates, a whole core, And what normally we do on whole core is all kinds of analysis. And whole core is actually very important because it contains as much description in volume of the properties of the rocks that we're looking at with conventional well logs. And here what I'm showing is two plots of density and photoelectric factor produced from the X-ray imaging of the carbonate. So we have 3D X-ray imaging, and one can see not only great variability by the naked eye, so to speak, but also through measurements such as X-ray analysis. Very important to do this in complex carbonates. It's also very important because once we look at these images, a decision is made as to where to take plots for laboratory analysis. And the plots, as you know, because the commercial systems that do laboratory analysis, they are based on specific sizes of the core plugs. Those are anywhere between 1.5 inches, 2 inches, perhaps an inch diameter. And maybe that size of core samples will not capture the variability that we need to capture in order to predict storage and flow properties. More specifically between wells when we subject these carbonates to primary production or enhanced recovery production. Now, it's also very important to remember the depth of investigation, the resolution that we have with the various tools. I'm going to be talking about borehole imaging. I'm going to talk about NMR measurements, and I'm going to talk about sonic logs and formation tester measurements. But it's very important to understand what is the vertical resolution of this measurement in terms of the variability that we have in the measurements or in the rocks. So let me begin by talking about borehole images. There are two borehole imaging systems that we use in formation evaluation. One is ultrasonic based imaging, and the second one is resistivity based imaging. They are complementary, but also we use them in conditions that are specific for the rocks that we are encountering. So let me be more precise. These systems, what we're going to do with them, with the images, is that they produce an image that tries to cover as much of the perimeter of the borehole. In fact, for the ultrasonic measurements, we cover the entire surface of the borehole. But for electrical resistivity measurements, depending on the size of the borehole, we have gaps between the measurements. But the idea is that once you cover as much as possible of the surface of the borehole, then the display that we have here is one in which we unfold the image. And so we always present the image unfolded, and to give some reference to the image, we oriented with respect to the magnetic north, the east north, south north, west north, and north north. So we have that. And also please bear in mind that if you have the intersection of a plane, of a Euclidean plane with a cylinder, the intersection is going to give rise to an ellipse. So if you have that ellipse and you unfold the ellipse so that it looks now on a flat plane, the intersection of the plane would look like a sinusoid like this. And the sinusoid will have a location of the peak and trough, and will also have an amplitude. The amplitude is directly related to the dip of the formation. So the larger the dip of the formation with respect to the borehole axis, the larger the amplitude A. And the azimuth, which is also another way of calling strike of this plane, will be based on the locations of the peaks and trough. So bear that in mind when we look at images, please. And here is a complementary plot slide of what I just said before, where we have this plane intersecting the cylinder. So we unfold it, and the unfolding itself is going to give rise to this sinusoid. And the dip that we have here, which is calculated as 6/12, that dip is going to be a function of the amplitude. And the azimuth of strike of this plane, it's going to be a function of the location of the east and west, and all reference with respect to north, east, and south, and so forth. Of course, these references are very explicit when you have a vertical well. When you have a horizontal well, we also have to think about up and down, left and right. That's another way of calling these locations. So please take this in mind, because we're going to see a lot of images in which the intersection and the surface of the borehole is unfolded. So we have to be able to understand what features we observe when we unfold the image acquired along the surface of the borehole. Okay, so here is the first device that we use, which is the ultrasonic borehole images. Ultrasonic borehole images are capturing the so-called impedance of the formation. And what is impedance? Impedance is a difference, actually better said, they capture the so-called reflection coefficient. And what is that? Well, this system, what it does is it sends an ultrasonic pulse. An ultrasonic because the frequencies are higher than megahertz. And so the wavelength is very small compared to the size of the borehole. So we send an ultrasonic signal. It's an acoustic signal with high frequency. And that signal is sent over to the formation. That signal, when it hits the formation, it's reflected. So what the measurements sense is the time of flight that it goes between when the signal is emitted by the ultrasonic source and when the signal is received back by the same piezoelectric transducer. Now, this system that you have here is rotating around the axis of the borehole, and because of that rotation with a certain speed causes the complete coverage that we see here in the figure. And so two things are recorded. One is the time of flight, and the second one is the amplitude of the reflection. Let me explain. When the signal goes out from the transmitter, it goes out with a certain amplitude, and then that pulse is reflected from the surface, and the reflection is going to cause reflection and transmission. So a fraction of the amplitude that impinges upon the surface of the borehole is going to be transmitted, and that the difference between the amplitude of the incident signal, or the ratio between the amplitude of the incident signal and the reflected signal, or the other way around, the amplitude of the reflected signal over the amplitude of the incident signal is what we call the reflection coefficient. And this is what we sense. It's a reflection coefficient that has to do with the impedance of the formation. And the impedance of this formation, acoustic impedance, that is to say, is a product of the velocity of P wave propagation and the density of the formation. That's what determines the amplitude of the reflected signal, the reflection amplitude. So what we have here are plots in these colors. Typically we have yellowish, reddish. And what it means is that when the reflection coefficient is high, the colors are going to be toward the yellow. And when the reflection coefficient is low, the colors are going to be closer to the dark that we have here. And that's how we can see features such as, for instance, solid rock, or soft rock, or rock that has holes. And the reason why this amplitude reflection is very small is because we have fluid there. So that's how we look at these signals. And again, the principle has to do with the velocity of propagation of P waves, compressional waves. So we're looking at the rock from the viewpoint of P wave velocity, from the viewpoint of elastic properties, if you will, from the viewpoint of mechanical properties. And so we're looking for contrasts in mechanical elastic properties of the rocks, and those are the contrasts that give rise to these images. And this is a beautiful example of when we have a fluvial system here, and the fluvial system, when you go through the borehole, we are going to see a multitude of stone sizes or rock sizes, grain sizes, gravel, for instance, conglomerates, and this figure over here is showing a photograph of this rock, and on the left we have the image. And the reason why we can see the differences between grains and not grains is because we have a contrast in acoustic impedance. If we didn't have a contrast in acoustic impedance, we will not be able to differentiate these materials. from the borehole image. So you see, we're looking for a contrast that visually can approximate what we see in this photograph over here. All right, and here are some examples of beautiful, magnificent ultrasonic borehole images acquired across the Edwards and Trinity groups here in the hill country of Texas. And what we can see is a number of very interesting features. Look at these sinusoids. Those sinusoids, as I said, they have to do, the amplitude has to do with the dip of the intersection of a plane with respect to the borehole axis. And when you look at these amplitudes, on occasion here, for instance, the amplitude is very large compared to the amplitude here. So that means that the dip is higher. And then look at the amplitude over here. That's a very high significant amplitude. So that means that what we have here is a plane intersecting the borehole at a high dip compared to the dip that we have here, or compared to the dip that we have here. Sometimes the fractures are oriented one way, look at this, and then they're oriented the other way. And then we have fractures that are open, and then we have fractures that are closed. And then we also have breaks up in the rocks. And then we also have these marks that are like railroad tracks, and those have to do with the drilling process itself. Drilling-induced fractures, but it's important to look at this. All of these features in the Edwards Aquifer are very important because the Edwards Aquifer here in Austin captures and moves water through fractures, through vugs, and so we have a great variability of features that enable the transport of fluids in this rock. And so when we look at these images, is very important because then we have an idea of which fractures are open and which fractures are closed. And please note that the reason why we can see fractures here is because of the impedance contrast with the surrounding rocks. So these are open fractures. All right. Now, second principle for borehole imaging is electrical resistivity borehole images. How does it work? Essentially what we do is we're looking at the electrical resistivity in a millimetric resolution across the borehole. And the way we do that is that you send an electric signal from the tool and using some pads as indicated here. And those pads are in contact with the formation. They're open, these arms are open, and they're pressed against the borehole wall. And the idea is that these arms are going to cover as much of the surface of the borehole as necessary. And each one of these arms is fitted with a number of electrodes. And those electrodes individually are going to be measuring the electrical resistivity of the formation. And by looking at all of these electrodes and putting them together, we are going to produce this beautiful signal that you have here. And this signal, what the images are showing, is electrical resistivity or electrical conductivity, whichever you want to work with. But all of these images, look at the gaps that we have here. The gaps in dark and light color are indication that there was no coverage of the borehole right there. And the reason why there was no coverage is because these pads are not covering the 360 degrees of the borehole surface. They only cover a section. And also the reason why these gaps are not straight, they're moving, is because the tool is rotating as it's acquiring measurements across. All of these tools, the tools that use or are used to acquire images, they have to run very, very slowly compared to the speed of logging that we have in the conventional logs. And this is one of the reasons why the service itself is very expensive, in addition to the large amount of data, and also in addition to the processing techniques that need to be applied to these measurements to render these beautiful images. So bear that in mind, and these images are acquired only across specific sections of the borehole. Because of their speed of logging, they cannot be acquired across the entire well. So we have to be very choosy and very specific when we request that these services be made. But in images like this, we're looking at the contrast in electrical conductivity, electrical resistivity between the rocks. And those contrasts, because of archery, they have to do with porosity, and sometimes they have to do with fluids. So I'll talk more about this, but bear in mind that we are looking at a different principle compared to the principle that we're looking at when we construct the images based on ultrasonic sensors. All right, and here's a close-up view of the tool itself. These are the pads, the opening of the arms that we see here. That opening is used to measure the caliper of the borehole, and the pads are intended to cover as much as the surface of the borehole as possible. Some of these are foldable, some of these are not. We also have a dead weight that tends to centralize the tool. And this is another look at the same tool. It's a larger version of this tool. Looks like a lateral lock tool. And here we have a close-up view of each one of these pads when it's in contact with the borehole wall, is sending electrical currents. And essentially what each one of these electrodes that we have mounted on the pad are individually and separately measure the electrical resistivity of the borehole wall. And that's how we construct the images. And the images, the colors that are done here, they use this sort of reddish, yellowish, dark pattern to present the images, but this is what we have to remember. So if you were to plot the individual resistivity of one of these pads, this is what it would look like. You will have high resistivities and low resistivities. What the tradition is for low resistivities to be plotted in darker colors, and high resistivities could be in lighter colors. So when you have a formation that has porosity and the mud filtrate goes into that porosity, then if the mud is water-based mud, then obviously the water saturation will be very high, and consequently the resistivity will be low. And that's the reason why we will tend to see those regions in dark colors. And when you have a rock that has no porosity, then because of Arch's equation, the resistivity will tend to be very high. And because of that, the resistivity will be high. The rendering of the colors, the min and max, and the saturation will depend on several ways of doing it. I'm going to explain that in a second. In fact, we have two ways of plotting these borehole resistivity images. One is a so-called static plot, and the other one is a dynamic plot. What is that? Okay, so what happens with the static plot is that you have a set of colors, 0 to 100 and 250, whatever number of colors you have in your printing device or in your digital device. And then what you're going to do is you're going to select the min and max, and the values or the colors are going to be linearly interpolated between the minimum and maximum. Another possibility is to use a logarithmic scale for that, of course. But yet another possibility is what we do call histogram equalization, which is you take a sample over depth of these values of resistivity, and then you draw a histogram and you do the cumulative density function of the histogram, and based on the cumulative density function of the histogram, you map the colors from min and max. And because of that, you have a more dynamic, less saturated color scale, and because of that we can better see certain features on the borehole images. So just bear that in mind, that very often these borehole resistivity images are displayed either with a static color scale or with a dynamic color scale. And here are two beautiful examples. Look at this. On the left we have a cave covering 3/4 of the borehole, and of course the fluid that we have in the mud has gone into the cave, and that's the reason why the color is dark, because the resistivity is very low. And why is the resistivity low? Because the water saturation is high. Then we have some other fractures here that are open, and we know that they're open because the fluid went inside them. Then we have also some other fractures that are aligned with the plane of sedimentation. So these will be the linear conventional scale, and on the left we have the dynamic scale. And here we have another beautiful image of a carbonate sequence. What I want to plot, again, we have the conventional linear image and the dynamic image. We can see the fractures. We can see that some of those fractures are open. We can also see that the bedding planes have a different cyclicity. And over here we have a plot of the dips that's on this x-axis, and the azimuth is given by the orientation of this tadpole. That's how we plot or present these results. And so we can see a lot of features in the carbonate sequence here. Let me show you another example. Here is a beautiful intersection between a classic sequence at the top, and then we go into the carbonate sequence. So what we see is that the resistivities across the classic sequence are much lower than the electrical resistivities across the carbonate sequence, and that's the reason why we also see a large contrast in the average colors above and below the unconformity. And now here is another section of this well that has a valvular carbonate. We have two sections, one section over here and one section over here that are valvular. And when you look at these sections with the dynamic scale, it's more obvious to see the vugs that are present in these formations. Another excellent example. And more examples of valvular carbonates. Here is the standard color image, and here is the dynamic image. And we can see that the vugs are open because the mud filtrate, water-based mud, went into this formation. I have to clarify that many of these instruments, the borehole resistivity instruments, work very, very efficiently when they're working in the presence of a water-based mud. If you have an oil-based mud, then the principle of operation needs to change because, as you know, oil is not electrically conductive, so we will not be able to see these features in the same way. In fact, there are new systems, very different systems, borehole resistivity images that are used when we have an oil-based mud. The resolution is not the same, and we have to use a different principle having to do with dielectric measurements. But I won't talk about that. The examples that I'm showing here today are all based on the presence of a water-based mud. And similarly, when we're using ultrasonic measurements, we have to be careful because some of these ultrasonic measurements are very, very sensitive to the presence of solids in the mud. So when the mud is very heavy because you have lots of barite or bentonite, when the pulses are being sent to be reflected on the surface of the borehole, some of that trajectory might have what we call scattering. And scattering, what it will do is will disperse the signal. And so the images will not be as focused as otherwise would be acquired without the presence of those solids in the borehole. Okay, now let's return to carbonates. Let's return to electrical resistivity images. So here's another valvular carbonate that has some stylolites that are present in some of these areas. But you can see the beautiful, beautiful variability of pore sizes that we have in this carbonate. And I want to clarify that some of this variability is three-dimensional. You see, please remember that the conventional well logs are taking an average not only in the vertical direction and in the radial direction, but also around the borehole. And because of that, we will not be able to see this incredible variability that we see with borehole images. So that's the reason why these are considered boutique logs, and you have to know when you have to acquire them because of the rock complexity. And here's another beautiful example of a brecciated carbonate, similar to what I showed in some of the movies for the part 2 of the carbonate trilogy. Here's a breccia outcrop, a carbonate formation, and on the left we have the corresponding borehole resistivity image. And here we have another plot of how, another photograph of how these brecciated carbonates look like, and in fact many of them are very good hydrocarbon reservoirs. And also please look at the variability of pore sizes, and the reason why the borehole images are able to see these openings is because the mud filtrate goes in there, and therefore the resistivity is very low compared to what we see in the yellowish section, which are sections that have no openings. And of course, one of the biggest issues on this when probing these carbonates is, for instance, if you see a hole like this one, the question is, how deep does that hole go? What is the length away from the borehole wall? And what is the density of these boreholes? And so we have to do a lot of statistics based on the well logs on the borehole images, and based on that we can have a better anticipation of what the pore variability in pore connectivity are away from the borehole. But definitely features like this, when encountered in the borehole, we have a big effect on the transport and storage properties of the rock. And here's another breccia, again the dynamic image and the linear image, and here is the corresponding core sample. We can see presence of hydrocarbons within the fractures or even within some of these openings. But this is a highly brecciated carbon. And here is another plot of a breccia and borehole images. And the most interesting, striking property of these breccias is that we have a lot of dolomitized limestone, and some of the blocks are so large in the breccia that they're even fractured, or they have their own pores within them. And that's an incredible important information to quantify the transport and storage properties of these rocks. Another very interesting structure is the one that comes with stromatolites. I showed a stromatolite at the beginning of this presentation, and here we have a borehole image, and the stromatolites are here where the cursor is pointing. Right there we have another one right here, or if you want to see them in the histogram equalized image, the dynamic image, look at this. And to be more specific, this is how a stromatolite would look like from an outcrop. These are algae mounds that grow in fresh water. In this example, they are coming from the opening of the Atlantic Ocean and these freshwater lakes. And they are beautiful structures, and much of the production, hydrocarbon production that comes from the deep water carbonates in Brazil comes from structure like this, from stromatolites. You can imagine what the pore size variations are, the pore connectivity, and so forth, so on. So recognizing the presence of these with conventional logs is very, very hard, impossible, but the idea is that only when you have high resolution logs like these resistivity images, we can understand their location and quantify their properties. And here is just to show you, remind you the block of stromatolites that I was photographing in Sao Paulo, Brazil, just to show you the striking resemblance that we have in these images. And here's another interesting image. I showed this outcrop at some point in the trilogy. Here we have chert nodules. If you go to Pedernales National Park or State Park, you will see a lot of the chert nodules like this within the carbonate blocks. And of course, these are very non-conductive features, so the scale will be, color scale will be very yellow because the resistivity will be super high, and that's how we recognize them in this beautiful image. That we also recognize that the layers have a dip and an azimuth. And here is another rendering of a well with extremely high transitions between the dips of the layers. We also have fractures that go through the layers. We also have fractures with high depth, and we also have breakup places. We also have bogular porosity, such as in cases like this, and structures in general extremely variable. It would be nearly impossible to recognize some of these features with conventional logs. Now, here's another beautiful image of fractured carbonates. And what happens in fractured carbonates is that we have primary porosity, which is the one across the fractures. You can see some of the imbibition about the wetting of the hydrocarbon going on in the immediate neighborhood of the fractures. And then we also have, say, primary porosity, which is the porosity across in between the fractures. And you can see the hydrocarbon being present there. And some of these features sometimes can be recognized in the borehole images. So another very interesting case for fractured reservoirs. In fact, fractured reservoirs are almost invariably analyzed with borehole images because of the importance of the fractures in the flow of fluids. Now, having talked about borehole images, let me get into another very interesting boutique advanced well log, which is magnetic resonance. Magnetic resonance, you will see in a second. The reason why we do it is because it gives you a very good description of the pore size distributions and the fluids. How does it work? The principle of magnetic resonance is based on the very important fact, and I mentioned some of these during the introduction of this video recorded lecture, is the fact that hydrogen nuclei are protons and they have a spin, 1/2 or -1/2. And because of that, they behave like magnets. And what does it mean? Well, it means that if you apply a magnetic field on them, they are going to be aligned with that magnetic field. The alignment is going to cause them to precede, and the precession is going to, or nutation if you will, is going to cause them to have a precession at a particular frequency, and that frequency is the so-called Larmor frequency. The frequency depends on the intensity of the applied magnetic field, and it depends on the molecule itself. In magnetic resonance, as applied to rocks, we focus only on hydrogen. Any atom that has an odd number, atomic number, will have this property of looking like a magnet. But because many of the fluids that we deal with in our business have many of the fluids that we deal with in our business have hydrogen, then we tend to focus our attention on the sensing of hydrogen protons. That only means that when we have an applied external magnetic field, the Larmor frequency is not only a function of the applied field, but also of the specifics of the molecule. And that frequency, we tune it already all the time to hydrogen. All right, now, what else? Well, what happens is this. If you do magnetic resonance, as I showed in the movie, over a sample of water like this, then you're going to find that without applying an external DC magnetic field, the effective magnetic field coming from all the protons here will be 0. And why so? Well, because they're all oriented in random directions. They are magnets, but they're all oriented in random directions. So what we need to do is we need to polarize them in a direction. This polarization doesn't happen instantaneously. In fact, there's a time or lag that we also use to quantify the time of magnetic polarization. So here it comes. Now, so that's how it works. We polarize them, and then we rotate them to a plane perpendicular to the original direction of the applied DC magnetic field, and then we force them, and then we turn off that source, that radio frequency pulse, and then because of that, they begin to do random walks. And the random walks, what they do is they're all aligned, they're all sending their magnetic fields, but when they experience these random walks, little by little, they are going to lose alignment, and the loss of alignment will send them back to their initial position of randomness, in which case the effective magnetic field emitted by all the protons will be 0. So what we measure is the time it takes for that magnetic signal comes from the population of protons to die, to decay to 0. And there are several physical principles that govern the decay of that signal. Sometimes it's a very fast decay, sometimes it's a very small decay, very slow decay. Sometimes it has to do with the pores, and sometimes it has to do with the fluids. So let me explain this. When we look at a piece of rock that has, let's say, 20% porosity, if we look at this rock with neutron density logs, we will not be able to say whether that rock has very large pores like these dos X beer, 20% porosity, or it's coming from small pores. And of course, we know that the difference between small pores and large pores, even though it's 20%, will make a big difference in the transport properties of these rocks. So we have to be able to designate this. What magnetic resonance does is, first of all, it measures the decay of effective proton magnetization as a function of time. And the decay can happen very fast or very slow. In the example of the dos X beer, the decay will be relatively slow. And in the case of the small pores, it will decay relatively fast. And both decays will begin from the maximum proton polarization possible, which is assuming that all the protons are distributed in the pore space, large and small. So what we have is a situation where magnetic resonance not only is able to quantify the porosity of the rock, in this case the Dos Equis, and the rock with the same porosity but with small pore sizes, but also is able to quantify the average pore size because of the speed with which the magnetization will decay as a function of time. And that's a very, very important thing. Of course, sometimes, actually often, the decay is also governed by the type of fluid. So we have to separate the fluid effects from the pore size effects. But let me be more specific about how this happens. So the way this happens, as I indicated in the video that preceded this lecture, is the fact that first of all we polarize all the protons, all these hydrogen nuclei. We polarize them with given direction and using a DC magnetic field. That is a magnetic field that the intensity does not change as a function of time. And then this polarization causes a relaxation because the polarization is not instantaneous. It takes a certain time before the polarization takes place. And this time, the time it takes for the polarization to be maximum, is governed by both the pores, the medium itself, and the fluids. So we have ways to quantify some of the fluid properties based on measuring the speed. For water, this takes place in about 3 seconds, the polarization. Now, second, after we polarize these protons, we do a second thing, which is the transverse relaxation. What is a transverse relaxation? Well, we send a radio frequency pulse to the protons, and the pulse is oscillating at a frequency equal to the Larmor frequency that we had before, when the protons were preceding because of the action of the DC magnetic field. And that will turn them into a plane perpendicular to the direction of the applied DC magnetic field, and they will be oscillating in that plane. So that's how we do. And then suddenly we turn off the radio frequency pulses. We turn them off, and when we turn them off, immediately the protons begin to do random walks in the medium. And the random walks in the medium will cause them to eventually, with time, to lose synchronicity, alignment. And because of that, as a function of time, fewer and fewer of the protons will be aligned in the same direction, perpendicular to the applied DC magnetic field, to produce effective magnetization. And what we measure is the time it takes for that magnetization to decay. And the time it takes for that magnetization to decay, it depends on multiple factors. But let me explain that. I just want to also say that the way in which this decay is measured, quantified, is based on a sequence of pulses governed by the radio frequency antenna that are called the CPMG pulses because of Carr, Purcell, Maybaum, and Gill. Now, the time of relaxation, the time it takes for protons to lose magnetization as a whole. We have a group of protons all magnetized with the same direction, but as a function of time, they lose magnetization because they're all now pointing in different directions. So what we're measuring is the time it takes for that effective magnetization to decay to zero. And there are several reasons why this can happen when the protons are doing the random walks after the radio frequency pulses are no longer sent. And one is, if the random walk is done through a constrained space, and the random walks are beginning to interact with the surface of that constrained space, and the surface of that constrained space has some magnetic materials, such as paramagnetic materials, then effectively the more bouncing off the walls that the protons have with those walls, the faster collectively they will lose alignment. So that's what we call the surface effect. The second one is the bulk effect. This is due to a fluid effect where we have proton-proton interactions as they do random walks. And these proton-proton interactions, essentially what eventually cause is a loss of alignment. And that proton-proton interactions are going to be a function of the type of fluid, how the molecule of hydrogen, how the atom of hydrogen is tied to the fluid that constitutes its pore space. For instance, you can have gas, and then with the kinetic energy of the gas, you will have one type of kinetic energy, and that effect will be one in terms of losing alignment. But if you have water, it would be a different kind. And if you have heavy oils, for instance, the tightness of the molecules will cause the polarization to be lost faster. And there's a third type, which is the diffusion effect. The diffusion effect only takes place when the applied external DC magnetic field is not constant in space, so it has a gradient. Because of that gradient, there's also a propensity of the protons to lose alignment faster than without that gradient. And the loss of alignment, because of the presence of that gradient, is by and large utilized to uncover, to explore the mass diffusion coefficient of the fluid in the pore space. So all of these three properties are contained in the analysis. So while the polarization time is governed by the fluids and by surface effects as shown here, the transverse relaxation is governed by three properties. One is the fluid itself, which we call the bulk, the surface effect, and the diffusion effect. So what we do is we measure the times of decays, and then we try to separate the effects due to the fluid and the effects due to the surface and the effects due to the diffusion. So here is a summary of what I just said about transverse relaxation phenomena. So eventually what happens is that we measure, this is the axis of time, this is magnetic proton magnetization, and we have maximum at the beginning with everything is polarized, and then we turn them into perpendicular plane, they do the random walks, and they lose alignment, and because of that their collective magnetization decays to zero. And what we measure is the time it takes for this magnetization to decay. And we assume that this is an exponential function. And so essentially what we're looking at is the time constant of the exponential. And as I said, that can be due to three effects. One is the surface effect, where if you have small pores, the decay is faster than when you have large pores. So technically this part is very important because it's the part that is going to allow us to designate, to quantify, to detect the pore size distribution of the rock. At the same time, if you have different fluids are going to also cause decays at different rates. And so we have to take that into account. And lastly, we have a gradient in the applied DC magnetic field. Then that gradient could also accelerate the decays, and the acceleration of decay is governed by several things. Among them is the mass diffusion coefficient. So we have to, and also the gradient of the applied DC magnetic field, and also the inter-echo time. So there are systems that are going to be functioning with this. Today I'm going to show you cases that have to do with the surface effect, which is the one that we use for estimating pore size distributions, and also the fluid effect. And sometimes we can separate the effects, sometimes we can't, and I'm going to talk about those cases. So here is a photograph of a magnetic resonance system in the laboratory. The way it works is the same principle. So we have a sample that we insert in the system, and the system has a magnet, and the magnet polarizes the molecules, and then we have a radio frequency antenna that begins to place the protons to oscillate in a plane different perpendicular to the original direction of the applied DC magnetic field, and we measure the decays. And we can also apply gradients. We can look at the time of polarization, multiple possibilities and combinations that can be done here. But the important thing to remember is the size of the sample. All of these systems are designed to take into account a certain size. And also the frequency of radio pulses is different for different systems. So here's an example of measurements acquired in that laboratory measurement. So on the left we have the time of proton relaxation, and I like to use logarithmic time because that better reflects the decay. And on the second axis, we have the distribution of relaxation times. So what happens here is that, in essence, we have what we have here is the time of decay. And please note that at early times, the value that the asymptote of these time decays is, when calibrated properly, is the value of the porosity of the rock. So we have a sample of different rocks: Indiana limestone, Berea sandstone, Boise sandstone, Mount Gambier limestone. And we can see that the Mount Gambier limestone is the one that has the largest porosity, followed by the Boise sandstone, and then the Berea sandstone, and then the Indiana limestones. And also their decays are different. So what we try to do is okay, so since we know that these time decays are governed by multiple things, what we try to do is to express these decays as a superposition of exponentials. And each one of those exponentials will have its own time constant. And what we do is, here we represent the distribution of time constants to explain these decays. And the distribution is such that these are the things that we do. If you do the area under the curve for each one of these distributions, that area under the curve will be the porosity of the rock. And it's important because please remember that in the magnetic resonance systems, we are looking at only fluids, because we're only looking at hydrogen atoms that can do random walks. So if you have hydrogen in the solids, well, they cannot do random walks when we applied all these physics principles. So because of that, even though we have hydrogen in the solids, we're not taking that into account. This is important because in the neutron and density logs, we're looking at all the hydrogen that we have, especially the neutron log. We're looking at all the hydrogen that we have in the formation, be it in the liquids, in the fluids, or in the solids. Whereas in the magnetic resonance, because of the principle of physics, we're only looking at hydrogen that exists in the fluid part of the rock. Okay, so we do the area under the curve, and that will be the porosity of the rock. Then, second, we are going to look at the distributions, and we look at the dominant pulse, or the dominant contribution. It's almost like you're trying to find what is the dominant time. Sometimes we have bimodality, sometimes you have unimodality, sometimes you have skewed distributions. When you have an asymmetric distribution, that means that you have a single exponential. But when you begin to have a distribution that is skewed, then that means that you are summing more than one dominant time pulse. And then that we have to interpret in a different way. And so that's what we look. What is the symmetry of this distribution? Second, what time do we have for the dominant peaks of this distribution? And third, what are the amplitudes of the dominant peaks? So that's what we look, and those are the properties that allow us to differentiate the different rocks in their pore size distributions. So here, for instance, we know that the Mount Gambier limestone is the one that has the largest pore sizes compared to, for instance, the one that has the smallest pore sizes in this example is the Berea sandstone, followed by the Indiana limestone, and then we have the Boise sandstone. And based on also the area under the curve, what we see is that the Mount Gambier limestone is the one that has the largest porosity. So by comparing the T2 distributions of these magnetic resonance transverse relaxation systems, we can understand the dominant pore sizes, the porosity, and whether the distribution is skewed or not. Those are things that we need to properly identify the pore size distribution and the effects that they have on the estimation of properties, fluid transfer properties. So here's an example of two rocks that have the same porosity, or closely same porosity, 20% porosity, and they have different permeability. So you have approximately the same porosity with different permeability. And why so? Well, because the throat sizes and the pore sizes are not the same. And why is this happening? Okay, so here we have, as I said, 20% porosity, and in one case we have 7.5 millidarcies, in the other case we have 279 millidarcies. And if you look at the T2 distributions of these rocks, which is on the x-axis we have T2 time, and on the y-axis we have proton magnetization. What you're going to find is that if you do the area under the curve of these two systems, you are going to find that the area under the curve is approximately the same, and that's the reason why the rocks have approximately the same porosity. But the dominant peak of the T2 distribution for the rock that has the largest permeability indicates that the decay time is slower than in the upper rock. And because of that, if the fluids are, in this case, just water, then what happens is that immediately we know that the dominant pore sizes of these rock at the bottom are going to be larger than the dominant pore sizes at the top. That's because of this is the surface effect. Second, we also see that the rock at the bottom has a bimodal pore size distribution. It has a second component right here. Whereas the rock at the top seems to have a dominant pore size, but we also see that the distribution is broader than the distribution at the bottom, and that has consequences for the distribution of pore sizes. So essentially, the dominant time of the T2 distribution will be an indication of the dominant pore size of the rock, and because of that, we can anticipate that despite the fact that these two rocks have the same porosity, they do not have the same permeability. And that takes us back to our favorite example of looking at these rocks as a shower head, where you can have either equal size of throat sizes or unequal sizes of throat sizes. Of course, the magnetic resonance principle is looking at pore sizes, not throat sizes. To look at throat sizes, we have to use the principle of mercury intrusion capillary pressure, for instance, but very often there's a correlation between pore sizes and throat sizes, and that's the reason why I invoke this example of the shower head to understand the differences in response here. So what is the depth of investigation and what is the resolution of magnetic resonance measurements? What I want to show you here is that magnetic resonance is indeed a very shallow sensing measurement, very, very shallow sensing. We're looking at 1.2 to 3.8 centimeters, and the vertical resolution is anywhere between 23 to 76 centimeters, depending on the system and the company that you are using, different principles. But I want to emphasize that NMR systems are extremely, extremely shallow sensing, and because of that, they're very often affected by the presence of invasion. All right, so here we have an example. This is a clastic formation, but I just want you to see what happens when they present the NMR logs. So what we have here is an x-axis when we present the magnetic resonance log, and that is a T2 time, the transverse relaxation time. And then we have each one of these depths has a plot like the one shown here, where the plot is a histogram and is represented with these greenish type of histograms, where what we know is on the x-axis is time of transverse relaxation in logarithmic scale. In the scale that we have here, it goes from 0.3 to 3,000. That's 0.3 to 3,000. And what we see here is and what we see here goes from 0.3 to 3,000, and 0.3 on the left, 3,000 on the right, and then we have the histogram. So what we're looking at is always how many dominant peaks do we have. Here we have two dominant peaks, here we have one dominant peak, and we're looking at when the dominant peak takes place, what time, because we know that early times will indicate small pores and late times will indicate larger pores. And of course, the area under the histogram will be the total porosity of the rock. And we're also looking at the amplitudes of these functions, these T2 distributions, as an indication of dominance. So what we typically do, that's the display we have, but let me go back to the samples we do in the laboratory. Here's an example of a Berea sandstone. Typically what we do is we saturate and this is what we typically do in the laboratory, is we saturate the sample 100% with water. And then once we saturate it with 100% water, we take a measurement of the magnetic resonance. Here, with this Berea sandstone, we see that we have one dominant peak on the T2 distribution. Here is the time decay itself. You can avert how many exponentials one needs to reproduce a signal, but we have a dominant peak. The dominant peak, as I said, is going to be governed by the fluid, in this case water, and also by the dominant pore size. Now, this distribution, the area under the curve, is going to be the total porosity. That's also the asymptote of this time decay curve. And then second, what we do is we take that sample, we centrifuge it, we expelled as much as the water so that air takes the place of the water that is expelled. And then once that happens, once the expelling has been completed, then we take another magnetic resonance measurement of the same rock. And here is the magnetic resonance of that rock after expelling the water. And then of course you do the area under the curve and you will get a different porosity, but in this case that porosity is smaller because in the air you don't have hydrogen. So the only hydrogen that you have is in the remaining water, and so essentially that porosity will be equal to the volume, the pore volume of the fluid that remains in the rock trapped because of capillary and clay-bound forces. And that is what becomes irreducible water saturation. And what this indicates is that this, in the dark blue distribution, where we had a non-symmetric distribution, it appears that this is actually the superposition of two dominant peaks, one for the larger pore sizes and one for the smaller pore sizes, and smaller pore sizes are the ones that are holding the water, not able to expel the water because of centrifuge. And so the differences between the pore volume of the sample at full 100 water saturation and the pore volume of water left after centrifuge, that will be something that we can harvest to estimate permeability of the sample. In fact, in many of the systems, what they do is they place a cutoff between what is movable and what is not movable. And some people actually in sandstones, in siliciclastic sequence, they assume that the cutoff is about 33 milliseconds. And so somewhere out here, and they say what is on the left of this blue curve is movable, and what's on the right is, what is on the left is not movable, and what's on the right is movable, and that difference gives us an entry to calculate the permeability of the sample. It is not that magnetic resonance measures permeability, because magnetic resonance does not measure permeability. It measures pore size distributions or fluid properties. But by looking at these differences between before and after centrifuge, we can indirectly estimate the permeability of the sample. All right, and here is another way of saying the same thing, that we have different amplitudes of decay for the two rocks. The amplitude of proton magnetization begins with the same values, but the decays are not equally fast. And that causes differences in the T2 median of the two distributions. In one case is 1000 milliseconds, in one case is 200 milliseconds, indicating that the average pore size in the rock at the top is smaller than the average pore size of the rock at the bottom, and that explains the differences in permeability. And again, what we try to do is to separate the fraction of this curve that is governed by capillary bound and clay bound water versus the portion of the water that is governed by movable water, and that discrepancy is going to give us an entry into possible ways to calculate permeability by different techniques. Okay, and here is an example of a log where, first of all, I want to show you what the effect would be of having different minerals. So this is the surface effect, the surface relaxation effect. So you can have pores with same sizes, like done here, but let's say that the pores are lined with different paramagnetic materials. In the case of siderite, we have iron-based minerals that are magnetic, and so whereas in the case of calcite, the second part of the rock, we have paramagnetic materials, but not in the same quantity and quality. So what happens is that even though you may have the same pore sizes, when you have the pores lined up with more paramagnetic materials, then the surface effects will be accelerated. And that's what this plot shows, that sometimes we have to also take into account the mineralogy of the rocks, because variations of minerals, especially paramagnetic materials, will also cause shifts in the dominant peak, not due to the size of the pores, but due to the variations of the minerals that are lying in the pores. Now, we have talked about this example before. This is a photograph courtesy my friend Austin Boyd, where we have a carbonate that has micropores, mesopores, and macropores. And when we look at this from the point of view of the pore size distribution, we saw a trimodal distribution. So if you do a magnetic resonance at 100% water saturation of this sample, you are going to see the relics, the suggestion of those three peaks, which is one peak. Of course, the area under the curve is going to be the total porosity of the rock. But the fact that this distribution is not unimodal, it has a dominant peak, yes, that's the largest peak, and this will be due to the fraction of the rock that is coming from the macropores. Then we have a second suggested peak here. You have to look at this in terms of their superposition, and that second peak will be due to the mesoporosity. And then you have a smaller peak here at earlier times that will be due to the presence of the micropores. So that's how we sense these properties in carbonates. When you have multimodalities, essentially what would happen with magnetic resonance is that the surface effect will give us three types of dominant pore sizes. And here is another plot, a related plot of another sample that we talked about in the part 2 of the carbonate trilogy, where we had a carbonate sample that had 30 porosity units and 97 millidarcies of permeability from Gawar, whereas in the lower case we have a waxstone that has 18% porosity and 8 permeability of 2 millidarcies. I was showing on this panel the corresponding mercury intrusion capillary pressure measurements, indicating that in effect the average throat radius for the upper sample is much larger than the average or dominant throat radius for the lower sample, and that explains why the lower sample has lower permeability. And now let's look at the NMR distributions, and what we see is for the sample that has a higher permeability, of course, the dominant T2 the T2 amplitude is larger than the dominant T2 amplitude of the sample that has lower permeability. Also, the distribution is not equally biased, is not equally symmetric. So if we were to partition the distribution into several symmetric quasi-log normal distributions, you will see that in this example you will need about 3 suggested here, and maybe you also need 3 here, but the average times in general, the average peaks of the T2 distribution here will tend to be lower times than here, and because of that we have the suggestion that the rock at the bottom, based essentially on the NMR T2 distributions, we will have the suggestion that this rock has lower permeability. So that's how magnetic resonance can help us to distinguish the pore size distribution of different complex carbonates, and therefore to give us an entry of the pore complexity of the rock. And here's a carbonate example where we have all the different logs. We have gamma ray logs, electrical resistivity logs, neutron density. We also have spectroscopy logs that are going to help us to designate some of these proportions of minerals. Here is highly a limestone distribution or a carbonate as indicated here. We have some anhydrite, we have pyrite in some of these examples, and we also have sandstone. So it's a combination of sandstone, clay, and carbonates. And then let's look at the corresponding T2 distributions, and those are the ones plotted here with the x-axis is 0.3 and 3000, minimum 0.3 and 3000 milliseconds. On the y-axis is a law, and on the x-axis already that's a logarithmic scale. Please look at the dominant peak. Here we have small pore sizes, and we can see that the carbonate itself is extremely, even though the composition is similar, the pore structure is not the same because the location of the T2 peak is extremely variable across the sample. And then we observe that the upper part is the one that has the longest dominant T2 values, and precisely that's where the permeability is the largest. And then we have sections with also we have high values of T2 in the T2 distribution, and that also indicates a higher permeability. So this variability of the location of the peaks will help us to understand what is the average or dominant pore size that we have in the rock, and because of that we can better predict the transport properties of this rock. And this yellow line is just here plotted as a reference to indicate the median, the location of the median pulse of the distribution. So just by looking at this, we will know that in the upper part the median pore sizes are very small. Here they're relatively high over here, and maybe smaller at another location. So this is just a different way to present the T2 distributions. And the permeability that you have here were all calculated based on imposing a cutoff between movable and not movable fluids for each one of these samples. And here is a calculation of the NMR porosity, which is the area under the curve. So you can see how porosity in some sections tends to increase and some other sections tends to decrease. But as I always say, and please, I hope you take this away, porosity is overrated, right? Because you can have a rock that has very high porosity in small pores, and then the transport properties of these rocks are not going to be very good. But you can have the same or lower porosity placed in larger pores, and then the transport properties of that rock are going to be better than even those of the rock that had higher porosity. So porosity is overrated, and what we have to always think about is pore size distributions and throat size distributions to properly understand the mechanics of storage and fluid transport in a particular rock. This is exceptionally important in the case of carbonates. And here is another beautiful plot, spectacular plot coming from some complex deep water carbonates. And what I'm going to show you, these are 3 wells in the same hydrocarbon field. And the gamma ray log for all these 3 wells is extremely low and flat, except here, which is an indication of presence of uranium. But you can pretty much accept that the shell presence is negligible in all these 3 wells. And second, you can also appreciate based on the plot that we have here in track number 3 is electrical resistivity, that the electrical resistivity values on the scale are very high, close to 1,000 ohmmeters, in 1,000 ohmmeters here. So these are extremely large values of electrical resistivity. And why so? Well, because the porosity of these rocks is relatively low porosity. That causes high resistivities. But the question is, okay, so this appears to be bad news that I have very low porosities. So how do I know that the rock is going to produce? Well, that's going to be a function of the average pore size. And what we see in this well on the left is that the average pore size is very large. That's very high. In the other rock, we see somewhat of a bimodal distribution, more indicative of a laminated sequence. And in the last one, and especially the upper part, we see that we have an extremely variable distribution of pore sizes. So if you were to compare these 3 samples or 3 wells, especially in the upper part, that have approximately the same porosity, you will find that the best transport properties will probably come from the well on the left because it has the cleanest and largest pore sizes, whereas in this sample in between will be average because you have, yes, good pore sizes, but you also have a laminated system, so the transport properties of this rock is not going to be as good as in the one at the left. And definitely the transport properties of the rock to the right will be the poorer because of the fact that on average the pore sizes are smaller. So now you can see that going beyond the conventional well logs and using magnetic resonance is a better predictor of transport properties of the rock because of this intuition relationship between distribution of pore sizes and permeability. Remember my analogy with the shower head. Good. And here's another way to explain the same thing, that we have rocks with approximately the same porosity, 15.1, 16, 11, and 14, but yet the T2 distributions are very different, you see. And the reason why T2 distributions are different is because the rock at the bottom will have the smaller pores, then the largest pores will be at the rock on the upper left corner, and then another one with very small pores here on the upper right corner, and then we have a sample that has a bimodal distribution of pore sizes. That could be because the rock is bimodal or because we're looking at a rock that has laminations. And that's the pore structure for the different rocks. Each of these yellow color scales is 2 millimeters. So here we have a rock with the worst and smallest pore sizes, and here we have a rock with the largest pore sizes. So that's important to remember. I also want to remind you that the T2, the transverse relaxation distributions, could be a function of the fluids. So a long time ago there was a very famous experiment carried out by my friend Chris Straley at Schlumberger, and what he did is he recorded the T2 distributions of a Berea sandstone with variable proportions of water and hydrocarbon, in this case kerosene. And what he found is that indeed there were two peaks, one for the water peak and one for the kerosene peak, and those peaks will have different amplitudes or relative amplitudes depending on the relative saturations of water. And so here we have plots of going from 100% water saturation, say rock, to 76, 57, 34, and 0, and then at the very end we have only pure kerosene. And at the bottom we have only water, so you can see how the presence of two fluids begin to split the distribution into dominant peaks. The takeaway from this plot is that in addition to understanding pore sizes, and that's good, pore sizes are very critically and uniquely and robustly inferred from NMR data when you have only one type of fluid saturated in the rock. But if you happen to have two types of fluids, then you have to subdivide the pore space between the two fluids before you attempt to describe the variability of peaks in the T2 distribution as due to variability of pore sizes. So that's important. And this happens a lot when you have, for instance, presence of mud filtrate. And I mentioned mud filtrate because, as I said, magnetic resonance is a very shallow sensing measurement. So because of that, likely the rocks that we probe are going to be to some extent saturated with mud filtrate. Okay. And this cartoon is just to remind you that we have the presence of grains, water, kerosene, and essentially based on the different concentrations, we're looking at the combined effect of the two fluids. At the same time, we look at the surface effects. Okay. Now, this is just a summary cartoon, a descriptive summary what to expect for the different fluids. And on the x-axis, we have the T2 distribution in milliseconds. When you have just free water in like in a bottle of water, it will relax at about 3,000 milliseconds. That's what we see. But as long as you put the water in the pore space, then the relaxation will vary anywhere between 1 milliseconds to about 300 or so, or more, let's say 700 milliseconds, depending on whether the water is in large pores or small pores. So the water is small pores, will be clay bound, capillary bound water, or free bulk water. And then for the case of hydrocarbons, the location of the dominant peak will be a function of the viscosity. So the super light hydrocarbons will have a very slow decay, and the super heavy hydrocarbons will have a very fast decay. So we have a whole gamut of possibilities here. And then in the presence of gradients, when the applied external DC magnetic field has a gradient, then in the presence of gas, we also expect a faster decay, which sometimes causes the gas signal to be below even the signal of oil. We have to take all of this into account for cases, for instance, when we have invasion with oil-based mud. So that's an important reference. This plot is done assuming that surface effects are similar to those of a clastic rock, that is when the grains are mostly composed of quartz. If the rock were composed of limestone, then essentially we will experience a shift toward slower times, because in some of these rocks and carbonates, the controlling effect of surface is smaller because the density of paramagnetic materials tends to be lower than in the case of clastic rocks. Something else to think about. Okay, so now let's talk about another borehole measurement that we can use to identify, quantify properties of carbonates, and this is borehole acoustic measurements. Sometimes this is referred to as sonic measurements, give or take. Acoustic measurements is probably a better name given the way in which the measurements are acquired. And here is how things work. We're looking at, when you do a borehole acoustic measurement, sonic logs, we're actually sending a signal, an acoustic signal coming from the borehole. The tool is immersed in the borehole, the tool is moving, and those signals are being sent. And what we measure is the time of flight that it takes for those measurements to happen. And of course, when that situation takes place, we can sense either the P wave velocity or the shear wave velocity of the rocks by using combinations of sources and combinations of processing methods that we use to analyze the recordings. And what we do is we have a tool that sends the pulses, acoustic pulses, and then we have a set of receivers. And then what we record are mini seismograms at every single depth, and from the mini seismograms we estimate the P wave velocity, compressional velocity, and the shear or S wave velocity of the formation. And this tool is moving from the bottom up, and when you do those measurements, the mini seismograms are processed real time, and we produce the logs that we have here, P wave velocity log or shear wave velocity log. Now, in a more specific context, this is what the tool will have. So we will have a sequence of receivers here, and then we will have a time of recording on the x-axis, and according to the number of receivers, this figure is exaggerated. We can have anywhere between 8 and more, depending on whether this is wireline or LWD. But we have some of the waves that come early, some waves that come late in different contexts. So the easiest, most common, most conventional way to do this analysis is to look at the fastest wave, the wave that comes the first. And what we do is we do some sort of coherence analysis to look at the fastest wave that comes through the array of receivers. And then based on the differences of time of flight between receivers and knowing the distances between receivers, we can estimate the corresponding speed of propagation. And the fastest time of flight is something that we will be using in this presentation. But before we go there, let me show you. This is the way a sonic tool looks like, where we have a transmitter right here, and we have some receivers. In this example, we have 4 receivers. And then we have a section here that is an isolated section with groups to prevent signals from traveling directly from the source to the receivers. And that's the configuration of the sonic tool. It's a tool that is centered in the borehole. Very important that it be centered in the borehole. So the acoustic signals that we record, they have to emerge from a fluid to reach the borehole. And when they reach the borehole, they excite the rocks around the borehole. And that excitation can be done in multiple ways. So here is another diagram of the tool itself operating in the borehole. And what happens is that we can have different types of sources. The most common source is called the monopole because it's an omnidirectional piezoelectric transducer that sends acoustic pulses in all the directions equally. And then we have a multitude of receivers. And the waves that we measured will vary depending on whether we have a fast formation. This one is a fast formation, and this one is a slow formation. And I know that it's slow because, you know, if you compare the waveforms from the top to the bottom, the ones at the bottom are coming later than at the top. And so we have a few waves that are coming here. Some of them are the P waves, some of them are shear waves, some of them are converted waves, some of these are Stoney waves. So I'm not going to talk about that. That would take a whole different lecture to talk about the different waves that we can record. But the most conventional way in sonic logging is to record only the fastest wave. And that was what was done at the beginning of sonic logging, the fastest wave. And the fastest wave is the one that leaves the transmitter and goes to the receiver the fastest, and that turns out to be a quasi-refracted wave, which we call P wave. And because of that, it's very shallow sensing, and that is the wave that I'm showing here. Is barely perceptible right here and barely perceptible here. So what we do is we estimate the speed of propagation of this fastest wave, and that is given by the slope here. We know the distance between the adjacent receivers, and by looking at the time of flight and also the slope here, we can estimate the velocity of propagation. Of course, this is slower than this one, as you can see. And that's what is done. So let's figure out what kinds of rock properties can one estimate indirectly by looking at these fastest arrival times. And just to remind you, as I said before, the depth of investigation and resolution of sonic logs is here, as shown here. The resolution is given by the length of the array of multi-receivers. And the depth of investigation is a function of the particular wave. But if you're looking at the fastest wave, that will be even shallower than 23 centimeters because it's a refracted wave. Okay, now when people were looking at this time of flight, the fastest time of flight, Wiley in 1956 came up with a very simple yet very ingenious way to explain what the fastest time of flight will be associated with in terms of rock properties. And he came up with this very simple time of flight average, in which he said, well, the easiest way to understand the time of flight, the fastest time of flight of these waves, is by partitioning the time of flight that the wave goes through, the solid component of the rock and the fluid component of the rock. And of course, the partition will be given by the fraction, the volumetric fraction of those two, which in this case is porosity for the fraction of the fluid, and 1 minus porosity for the fraction of the solid. So if one knew what the time of flight would be for the matrix and what the time of flight would be for the fluid, just by measuring the total time of flight, we could possibly estimate the porosity. And he called this the sonic porosity by doing this. Of course, nowadays we have a whole great, wide, deep field of rock physics that studies these relationships between time of flights, velocities, and all the different properties of the rock that have to do not only with porosity but also with fluids, and also they have to do with pore aspect ratios, with properties such as the viscosity of the fluid, poroelastic theory. This field of rock physics is very deep and very wide. So I'm not going to talk about that today, but I'm just going to focus my attention of the super simplest time of flight partitioning that Wiley came up with, because this you will see in a second that is very important, or at least useful, for the analysis of carbonate rocks. Okay, so just to remind you, the porosity of a rock is calculated from the density. We have this partition, this volumetric material balance partition that gives us an entry in porosity as long as we know the density of the fluid, the density of the matrix, and we measure the density of the rock. Similarly, for sonic porosity, we have the same partitioning system. Please note that I have called this sonic porosity. This is not porosity, it's called sonic porosity, and it's just the partition of the time of flight. So as long as we know the time of flight through the fluid and the time of flight through the solid and the measured time of flight, which is the fastest time of flight, then we can indirectly estimate this sonic porosity. Now, I have to warn you at the beginning, some people said that this sonic porosity is a measure of, what is it, the connected versus non-connected porosity, or what is it called, the isolated porosity versus not isolated porosity. Let me just explain that that's not true in most cases. Sonic porosity is just a very simple way to partition the time of flight, and it has consequences. So never use sonic porosity in place of porosity, although I have to tell you that there are many rocks in the world where if you calculate the sonic porosity, it will be very, very, very close to the total porosity of the rock, especially in clastic formations that are very tight. The lower the porosity, we know that the lower the porosity, the more accurate this sonic porosity will be compared to total porosity, or the closer the sonic porosity will be total porosity. But there are cases when the porosity is high, or when the fluids are mixed, or when we have fractures, or when we have different aspect ratios, or when the rock is anisotropic, that all of these things are going to vary considerably. And that's the reason why people who do rock physics study these properties in great detail. Another situation is when you have shale or clay. They tend to have very non-conventional ways to affect the rock properties, elastic properties of rock. So that's the reason why we have to take all of these with a very big grain of salt, please. But let me show you one example. And this is one way to calculate the sonic porosity, very simple way. And this is the way we're going to use for some of the exercises. The chart that I'm showing here is very similar to the charts that we use for PEF density and also for neutron density. And it's a sonic neutron sonic cross plot, which is port 20 for Schlumberger. On the x-axis we have the neutron log in limestone porosity units, and on the y-axis we have the sonic fastest time of flight in microseconds per foot. And we have the three guides, which are similar to what we did before. This is the quartz guide, the calcite guide, and the dolomite guide. And what I've done here is I expanded the scales, and one of the most important outcomes of this chart, if you will, for me at least, and I hope you also see, is that if you wanted to know what is the delta T, the time of flight for a given solid, it's very simple. You go to the end of the charts. This is for dolomite, this is for limestone, and this is for quartz. You can see that the fastest time of flight is for dolomite, that's the most rigid, and limestone, and then quartz. But if you go to the point 0 of the guide, that means that you have 100% solid. So if you project that point to the left, that is going to give you the corresponding time of flight for either quartz, limestone, or dolomite. So you don't have to memorize any of this, but that's one of the takeaways from these charts that I always use. And now you will see that there are two guides. One is the blue and the other one is the red. It turns out that the red is some sort of guide when you have compaction effects. Let me talk about that later. But for now, let's just concentrate on the blue guides. Okay. And also I want to mention that these guides are calculated using Wiley's equation, the time of flight average formula, assuming that the time of flight for the fluid is 190 microseconds per foot, and that corresponds to water. So the assumption is that you have water in the pore space. This is actually very commonly the case if you have, for instance, invasion with water-based mud. It's very likely that this will be the proper value for TF. If not, you have to make corrections. But we use that as a way of reference. Okay, and that's how these plots were calculated. In fact, if you go, say, for instance, to a given time of flight 80, and then you project it over to any of these spines, you're going to find that the point of intersection is precisely the sonic porosity calculated with Wiley's average, if you assume that you have only one component, and if you assume that that fluid is water. Then that's the graphical realization of Wiley's equation, which is the time of flight partitioning between solids and fluids. Okay, so now how do I use this property? Very simple. Let me show you one example. But the mechanics of this is that we always estimate total porosity with nuclear resistivity measurements, the way we have done it properly before, and then by using combinations of neutron density and doing all the corrections that we have, especially when you don't have shell, square root of the average of squares, all of those properties that we discuss at great length when we discuss dominant mineral composition. And then we're going to calculate the sonic porosity. And how do we calculate the sonic porosity? First of all, for reference, we're going to assume that water is a saturating fluid, and we have good reasons to do this. If you are at if you have some confusion as to why this, just go and calculate this in the aquifer or at a place where you have very deep water-based mud filtrate invasion, so most of the fluid that we're sensing is mud filtrate. Second, we're going to compare the total porosity to the sonic porosity. This is where things get interesting. And many times the difference between total porosity and sonic porosity is not going to be negligible. So how not negligible? So this is where we are going to calculate the percent difference. And if you have a small percent difference, maybe you don't have to worry about this. But if you have a large percent difference, then we have to start understanding why we have that difference. And this is where things get interesting. It turns out that that difference in percent in carbonate rocks could indicate pore heterogeneity. That's important. It could also indicate that you have bogs, differences in the rigidity of the rock, fractures, for instance. All of that is possible. In clastic rocks, if you see a difference, it's not only that, it could also be compaction, unconsolidation, and many other things. So we have to use that difference in the percent sense to diagnose indirectly variations in the rock properties, in the elastic rock properties of rocks. So here's an example. If you look at the time of flight, the fastest time of flight for this microfracture rock, we have a fracture right here, and we have the matrix, the dominant matrix. So when you send an acoustic pulse from the left, let's say from here to the right, and you try to figure out what is the fastest time of flight of this rock, then obviously the fastest time of rock for time of flight for acoustic waves will be to go through the section of the rock that is the most consolidated, the most rigid. That's how the time of flight is, that the rocks are going to choose the path of propagation that is the fastest, and the fastest is through the section of the rock that is the most rigid. And that's the reason why if you calculate the neutron and density porosity, the porosity of this rock, you're going to get the total porosity. But when you calculate the sonic porosity, essentially you're biasing your calculation toward the section of the rock that is the most rigid. And that's the reason why when you see differences between the sonic porosity and the total porosity, that signals something. So we have to be able to understand what signals. And fractures is a very common way to diagnose this, especially if the fractures are open. So that's number one. Second, suppose that you have a vuggy carbonate, and then again, you have an acoustic signal that you're sending from A to B here. And then the propagation is going to choose to go through it's the fastest time of flight, so the propagation is going to go through the most rigid part of the rock. So therefore, when you calculate total porosity based on neutron and density logs, you get one value. And then if you calculate the total porosity based on the sonic logs, you're going to get another value. And probably the sonic porosity will be lower than the total porosity because it's reflecting propagation through the most consolidated, most rigid part of the rock. And then we have to look at those differences, and based on those differences, we have to, it's a flag. It's essentially, this is telling you, be careful here, we have a big difference in percent, so there might be something heterogeneous about these rocks. So that just tells you that you have to go back and analyze those rocks and see why is that we have such drastic differences or non-negligible differences between sonic porosity and total porosity. Okay, now let me show you examples. This example we covered before. It's an example that is on pages 13 to 15 of PGE358 well log compendium. Part 2 is this Smackover formation that we mentioned before. And here we have the different logs, the gamma ray log, resistivity logs, neutron density logs, and sonic logs. So let's go ahead and first calculate the total porosity of this rock based on the neutron density logs. What you're going to see in a minute is that based on the neutron density logs, and we don't have PEF here, we're going to find that the dominant mineral composition here is dolomite. And then from that, we can calculate the porosity. If you do that, you're going to find that this is mostly dolomite, and it has a porosity of about 23%. Please note that because of the resistivity logs, we know that this rock is permeable. Now, how do we do that? Well, look at the neutron and density cross plot, the Schlumberger pore 11 cross plot. If you measure the neutron log in limestone porosity units, and if you measure the density log in limestone porosity units, then they intersect right here in the dolomite guide, and the intersection is 23%. That's how we calculated this porosity. Okay, now what about the sonic porosity? Here's how it's going to work. I go to the chart that I mentioned before, and then we measure the sonic log. So we go back to the log here, and we measure the sonic log right here. Okay, so we measure that. And that value is going to be 66 microseconds per foot. That's what we measure. Okay, so just remember, the time of flight for, this is delta T, the time of flight for the fluid is 190 microseconds per foot because we're assuming that is water. This example, you can see that the reason why the point falls in the dolomite, despite that this formation is hydrocarbon saturated, is because it's deeply embedded with water-based mud. Okay, good. So that helps us in the analysis. Now, we know that it's dolomite, so from the analysis of the neutron density porosity logs, so what I'm going to do is I'm going to go to the dolomite spine here, and I'm going to read the delta Tm for the dolomite, and it happens to be 43.5 microseconds per foot. And then we're going to calculate the Wiley porosity, very simple, from that partition formula. You can do it graphically here if you want. That's how I got this value, and that gives you 15.5%. Wow, so look at this. Just to remind you, the neutron and density porosity is 23%. That's the total porosity. And then the sonic porosity is 15.5. Much lower than the total porosity. In fact, if you calculate the difference, you're going to see that the total porosity is, the difference in porosity is about 32%. So 32% is the total porosity higher than the sonic porosity. Or it could be minus 32% if you calculate it the other way. But essentially we have a significant difference. That's not negligible. And then we have to find out why is that we have that discrepancy, that the sonic is giving us 15.5% and the total porosity is giving us 23%. So why is that deficiency that the sonic log is? And then that signals there might be a difference in rigidity of the rock within the volume of investigation of this tool. And lo and behold, this borehole resistivity image is from a different well, but just illustrates the reason. If you look at the borehole image for a section of the well for the same formation in a different well, you're going to find out that these two rocks are bogular. So we have a significant component of valvular porosity. And that is the reason why the sonic porosity is favoring the most rigid component of the rock. And that's the reason why we see a difference between the sonic porosity much lower than the total porosity. So with this example, I just want to point out that that difference, the delta porosity that we see between the total porosity and the sonic porosity, is signaling the possibility of heterogeneity of the rock. And that's how we use the sonic porosity, simply to give us a flag. And then we do further investigation to understand what causes this difference. Now, let's look at a case. I know we're not talking about clastics, but let's look at a case of clastics just to mention an analogy, okay? This is just for analogy. And this is an example of pages 1 to 3 of the well-logged compendium. This is the Gulf of Mexico example where we have spontaneous potential, gamma ray log, caliper, resistivity logs, neutron density logs, in Sanson porosity units, and then we have the sonic log. So what I'm going to do is I'm going to look at a section of this rock that is as clean as possible, where we have water. This is in the aquifer, and I'm going to read the porosity. If you do this analysis, you are going to find that the rock has about 35% porosity. And the delta T of the rock is the sonic time of flight is 117 microseconds per foot. Okay, so those are the readings that I have for that particular section. Now, if we do the analysis of this rock, Wiley's analysis, so here is the time of flight. In fact, the time of flight is so large that it's way out of the scale. But I'm going to extend the scale anyways, and I'm going to extend the guide anyways. Or I can use Wiley's equation. Forget about extending. I use the equation, the partition time of flight. And I have that because it's mostly clastic. I know what the delta Tm is, and it's 55.5 microseconds per foot. And then again, we use the delta T for the fluid, which in this case is water. Notice that we're in the aquifer. And then you calculate Wiley's. And what is that you find? What I find is that the sonic porosity is 45.7, whereas the total porosity is 35%. So this is giving us higher porosity. You see, in the case of carbonates, we had sonic porosity lower than the total porosity. Now, in this example, for this particular example, I'm finding that the sonic porosity is larger than the total porosity. And how large is that? Well, we're looking at a factor of 30%. So this is not negligible. Maybe the sign could be plus in this case, depending on which one you use as reference. But anyways, so we have this sign, and the question is why? And in some of these cases, actually in the deep water Gulf of Mexico, where we have unconsolidated formations, this is typically the effect of compaction. And that's one of the ways that we use this Wiley's time of flight average formula just for diagnostics. In fact, there are some folks that worked on this equation, and they found that to make the Wiley's time of flight porosity equal to the total porosity, they could include a so-called compaction factor here. And that compaction factor, of course, has to be higher than 1 to make the sonic porosity lower and lower. So essentially you find out what number you need to plug in here to make the value of the sonic porosity that you find equal to the total porosity, and that value will give you an indirect indication of the compaction. And that's one of the techniques that people use for reconciling the differences between sonic log, sonic porosity, and total porosity in clastic sequences. This is just an example. But in most clastic sequences where you have good consolidation, cementation, and the rocks that are not over-compacted or under-compacted or over-pressure, you're going to find that the lower the porosity of the clastic sequence, the closer the total porosity is to the sonic porosity. And that's the reason why in some fields, hydrocarbon fields around the world, or even in some aquifer geohydrological activities, folks use the sonic porosity in place of the total porosity because it's cheaper and also faster to implement. Okay, so now we know what to do with sonic logs. Just remember that. Now, let's move to another interesting subject, which is wireline formation testers. I just want to say that wireline formation testers are also widely used in carbonates to assess flow properties. And they have come in many types of possibilities, depending on the particular properties of the formation. For instance, mini drill stem testing, which we use widely to probe formations in the rock, they're widely used in the world to assess effective producibility of formations. So the formation testers, they were initially based on that same principle of drill stem testing, and we have a number of configurations: repeat testers, pump out tools, or straddle packers. I'm going to be talking about straddle packers in this section because of some very important technical context. But as formation testing technology evolved, we began to have different configurations of formation testers. These are tools that you press against a borehole wall, and when you press against a borehole wall, essentially you begin to withdraw fluids. And what we do is we withdraw fluids and we sample how the pore pressure changes as the fluid withdrawal takes place. And then we also do build-up, which is you stop the withdrawal and you look at how the fluid pressure equilibrates back. And there are many ways in which this can be done. Oval probes, for instance, when you have formations that are extremely heterogeneous, or we use dual packers. And dual packers, essentially what they do is isolate the section of the well that one wants to analyze, and that section of the well we have flow that is coming equally in all the radial directions. And we do this when you have a large segment of the formation, the amount of fluid that we work with is large, or the formation itself is very heterogeneous, so we want to analyze this transient pressure using a larger volume of investigation. Okay, and here are more probe geometry. Some of these are focused probes for ovalized or not ovalized. Different companies, different logging companies have the different tools. The reason why we also have different types of probes is because sometimes, very often actually, these probes are used to sample fluids from the formation, and at some point you have to separate the fluid that comes from the mud filtrate from the fluid that comes from the original formation before invasion. And depending on the viscosity of the fluids, depending on the properties of the formation, different probes are going to work faster or more in a more optimal way for those cases. So the dual packer is actually a very interesting thing because, as I said, you isolate the borehole with these packers, and then you have a pressure pump that works by bringing fluids toward the center of the tool over a very significant section. In this case is 3 feet. So the fact that it's a 3 feet length provides the possibility of analyzing a larger section of the rock. Of course, the storage that you have from the borehole is a little bit larger, but we have ways to contend with that. But that's important because you're enforcing radial flow, or you try to enforce radial flow, which is important. It's easier if you're trying to accomplish a volume of investigation that is equal around the perimeter of the borehole. And there are many configurations, but essentially the volume of fluid that you sample with this tool is larger than when point probes, and therefore the test may take a longer time to implement. And one of the common applications of this is for fractured rocks or rocks that have great variability in pore sizes, such as breccias, buvular formations, extreme cases of pore size distributions that require a larger volume of inspection to capture them in the flow regimes. And here is a close-up view of the point probe going on one side of the borehole, or the probe that is looking equally around the borehole, the dual packer. The way these tools work, I'm going to show you the general principle, but the way these tools work is the following. So they come to the borehole, and they have a pressure gauge. That's an important point, the pressure gauge, and they have a flow line. So the first thing that happens is that the tool is fixed in the borehole. This is a stationary measurement. The tool cannot move when you make this measurement. You select the point of analysis, and then you, first of all, you equalize the pressure by opening the pressure and looking at the fluid pressure that you have in the borehole. That equalizes the pressure. Then you extend the probe, the packer, with 2 pistons. You secure it. It has to be very nicely tight. And so the piston goes, and this is the probe. And this is where the fluids are going to be sucked in with the pump. So we have a pressure pump. And the pressure pump right here is going to withdraw the fluids. When the fluids are coming, they go into the pressure line, and some of them might be expelled. And we measure the pressure of those fluids, but some of them might be expelled. Or when the probe finds that most of the fluid that is coming is original fluid, not mud filtrate, it can also be placed into some containers, vessels, that keep them at in-situ conditions. That's also possible. So those are the sample chambers. So that's how it works. And then this works over time. And as I said, the probes can be different. Some probes are optimized to have the ability to better sample the fluids, or to more quickly sample the fluids, the in-situ fluids, so that you get rid of the mud filtrate as soon as possible. And here is the typical plot that we have. So the x-axis is time. This is the flow rate enforced by the pump, and this is the pressure axis. So at the beginning, we have the hydrostatic pressure coming from the mud line. And then the packer is set toward the formation, and then we begin to withdraw fluids, and the pressure decays. Then we stop withdrawing fluids, and the pressure increases. And it increases, and that's the final point is the pore pressure. This is the formation pressure. Very important. That's what we sample as formation pressure. And the time it takes for the pressure to stabilize the formation pressure, it could be like this, it could be like this, or it could be very fast. So it turns out that the time of stabilization, similar to the T2 distribution, by the way, or the decay of proton magnetization, this is a diffusion process. So it turns out that the time it takes for the pressure to stabilize is a function of the mobility. And the mobility is, of course, the ratio of permeability over viscosity. And that's how we use to, that's actually the notion that we use to estimate not only the pore pressure of the formation, but also the mobility of the formation that has consequences on the transport properties of these rocks. And then these pressures will be taken in a way that depends on the permeability of the formation. So now, what happens when you do this test of a very impermeable rock, less than 1 millidarcy? So let me just guide you through this. So first of all, we open the valve, we compensate, and we are measuring the hydrostatic pressure coming from the mud column. Then we set the packer. That's the initial point, and you will begin to pump fluids into the probe. And that's where the pressure drawdowns. Of course, we have to take into account also the storage that goes in the flow line, especially when you have a compressible fluid. And it decreases. And then you stop the pump, and then you let the pressure equilibrate. So you build up. And that's where you sample the pressure at that point. What I want to point out in this diagram is that when you have a very impermeable rock, this can take a very long time. Sometimes you have to be there for hours. When you have a very permeable formation, this can happen extremely fast. So you only have to be there a few minutes. But that time evolution is the one that we're going to use to estimate the mobility of the formation, which in the case of carbonate formations, it is very important because we're actually looking at this rock on their very large volume, larger than you can even attempt to do with core blocks. You see, so this is an in-situ mini transient pressure analysis to understand the different flow regimes and also to understand the average fluid transfer properties of the rock. And here's an example of samples done where you are doing multiple cycles. This can be done on multiple cycles of build up and drawdown to basically clean the flow line and also to make sure that the probe is making proper contact with the formation. So you do a few of these cycles until everything has stabilized, and this is when you do the build up and drawdown. And then once you have the section of the curve that you like, then you can do more specific and more detailed analysis, such as looking at the log-log derivative plots to understand flow regimes, and also at the Horner plots. These are widely used to understand or to infer properties of the rock. You can have, for instance, a rock that is anisotropic and you have one type of flow regime, or you can have a rock that has a pressure shield or an impermeable barrier. You will see a different thing, or a rock that has extremely large variability in properties as a function of radial distance away from the borehole wall. You can also examine those from the log-log derivative plots. Okay, and this is just to show you that there are techniques, analytical techniques or numerical techniques to match the pressure measurements here in terms of mobilities or in terms of other properties of the formation, geometrical properties and petrophysical properties. So by doing inverse methods, which is matching the measurements with numerical simulations, we can infer the properties of this rock. And that's how we do in pressure transient analysis. After that, after understanding the flow regimes and also the effective permeability of the rock, especially with the dual packer in very complex carbonates, we can also look at pressure gradients. And the pressure gradients will be an indication of connectivity, whether all of these formations are hydraulically connected or not, and presence or not presence of pressure seals, and also presence of different fluids in the rocks. So for instance, in this complex carbonate formation, what we see is we have different compartments over here, but we also see different fluid densities, that slope of the gradients. And the fluid densities can help us to understand the origin or the stratification of the fluid properties based on the existence or non-existence of pressure seals and maturation, and also of release of hydrocarbons from the source rock. So a number of possibilities can be done with these formation testers. Now, please remember that I mentioned these formation testers because it's important to remember the scale of investigation, the volume of investigation. And when you have rocks that are extremely variable like these ones, you want to make sure that the volume of investigation of your measurements is consistent with the variability of the rock. And that's the reason why for cores we have variability, very minimal variability, small pore sizes. And then you have small sample sizes, minimal variability, but then logs have a greater variability. And then the repeat formation testing that we're using, or the formation tester with the dual packer, can achieve longer distances. And finally, well testing. So it's important to understand that these dual packer systems can bridge the gap between the volume of investigation of a well testing, self-interference or a cross-interference between wells to understand communication and effective flow regimes. So formation testers are particularly important in carbonates because of their variability. And that's the reason why I talk about dual packer formation testers as a way to estimate flow properties of these extremely variable rocks. Now, let me talk about very quickly, the last advanced boutique log that we often use in carbonates. So I mentioned that in carbonates, sometimes we can have great variations in mineralogy, combinations of different minerals such as dolomite, calcite, well, not only that, in hydrite, siderite, many other possibilities. So because of that, it's important to have a nuclear measurement that has more granularity, that has more sensitivity to different chemical elements. And this is measurement spectroscopy is based on the fact that we take advantage of the gamma rays produced, and their energies produced from the interaction of neutrons and nuclei. So here is a tool that has not only the density tool, but also has 14 MeV neutrons as a source. So this neutron source is going to send high energy neutrons, 14 MeV, and those neutrons are going to interact with the formation atoms. So these fast source neutrons, and then we have epithermal interactions that are going to give rise to high energy gamma rays. Those high energy gamma rays are going to help us for understanding better the carbon oxygen, for instance, as one of the applications. And then as neutrons begin to lose energy, they are going to withstand elastic collisions, and those collisions are going to reduce the energy of the neutrons until they reach the so-called thermal threshold. And when they reach the thermal threshold, the neutrons are going to be captured by the atoms. And when the atom captures an extra neutron, it becomes radioactive, and it begins to send gamma rays whose energy is indicative of the atom that gives rise to this. So what these spectroscopy tools look at, they look at gamma rays that are produced as a consequence of the interaction of high energy neutrons with formations, and they look at gamma rays that produce at the high energy spectrum of these interactions, or at the very low energy, which is the thermalized spectrum, thermalized regime of interaction of neutrons with matter. And by combining all of those, these tools can provide a gamma ray counts for different energies that at the same time are mapped into counts for different elements, and from that one can map them into mineral compositions. So just to remind you, with a different plot, I showed this plot before for understanding dominant mineral composition in rocks, that we have a neutron sent at high energy. That neutron is going to interact with atoms, is going to lose energy. At the high energies is going to release inelastic scattering. That's what I have over here. And those are going to be high values of gamma ray over here. Gamma rays with high energy. And then they will continue to lose energy and so forth until they become thermalized. And when they become thermalized, then essentially they're going to be captured, and when they capture, they're going to be sending gamma rays. And the gamma rays, when they're sent, are going to be subject to photoelectric scattering, pair production. Well, not in this case because the energy is not sufficient. And Compton scattering and photoelectric absorption. And those are going to be the phenomena that we're going to be looking at as a way to infer the composition of the rock. And that is the principle that we use. This principle actually is the same one that I described in some detail in the nuclear presentation. So as an example of these plots is that now we can have more granularity, for instance, here in describing different minerals: pyrite, anchorite, dolomite, calcite, orthoclase, quartz, especially in very complex formations where you have not only carbonates, but you have also clastic rocks. I showed you previously the example of these chert, and chert is quartz. So essentially when you go through these formations, carbonate formations, based on these analyses, you have more granularity to understand and to detect presence of abnormal mineral compositions, such as in the case of chert, that would indicate a high concentration of quartz. And we also have more granularity to define smectite, illite, and properties. And these properties can have basic elements. For instance, here we have a group of elements: silicon, calcium, iron, magnesium, strontium, potassium, aluminum, titanium, manganese, TOC, organic material. They can be verified against, for instance, core measurements that come from XRD, X-ray diffraction tomography, or any other measurement that is done in the laboratory to estimate proportions of minerals. Now, when all of that is done, then we have a very granular description of very specialized minerals such as this, or minerals like this. And that variability can also help to understand why certain sections of the rock have more or less porosity, or more or different pore connectivity, flow barriers, for instance. So in essence, having a more well-defined distribution of mineral composition can also help to better define the transport and storage properties of these rocks. That's the idea behind doing a better definition of mineral compositions. And that's all with this part 3 of the carbonate trilogy. So I hope that I convince you enough that in some of these complex carbonates it's necessary to use advanced borehole measurements to quantify storage flow and mechanical properties. Core plugs are often too small to capture the variability of these rocks, and therefore they're not very good to predict rock or fluid transfer properties of these rocks, because the effects of flow barriers or storage and flow come from very large features that are larger in size than core plugs. I show you how borehole images, be them ultrasonic or resistivity images, can help you to capture the pore variability, which is not properly captured in conventional logs. Especially we need these measurements in key exploratory wells that can serve as reference for extrapolation of properties in other wells that have only conventional well logs. And I show you how magnetic resonance is an ideal borehole measurement to quantify pore size distributions in carbonate rocks. But we have to take into account the fact that magnetic resonance is also sensitive to surface relaxation, which has to do with mineral composition, and it's also sensitive to presence of different fluids. We have to take all of that into account before we transform the transverse relaxation measurements into pore size distributions. I also show you that sonic logs can be used to flag, to identify places where carbonate rocks may have pore heterogeneity, or strong variations in pore in rock rigidity that could be associated with variations in pore structure. And please don't use sonic porosity to calculate isolated porosity. That's nonsense, and it should have never been promoted that way. I also show you that formation testers, especially dual Packer formation testers, are optimal devices to sample fluid transport properties of carbonate rocks. And last, I show you that spectroscopy logs are often necessary to diagnose very granular and fine variations of mineral compositions of rocks that are not necessarily or reliably quantified from or with conventional logs. And then I have a couple of review questions. Well, actually more than a couple. So I'm just going to leave this open here for a couple of seconds to reflect on the main arguments and concepts that we discuss here. So please try to answer these questions as best you can. They're all based on the analysis that we did here. For instance, can magnetic resonance log sense presence of carbon dioxide? And well, you know, there's no hydrogen, so is it possible? Okay. and things of this sort. And the second page has a few more questions, especially concerning the sonic logs, the usage of sonic logs, the concept of sonic porosity. I'm also probing understanding on the usage of formation testers to capture properties of carbonate rocks, and so forth, so on. So please try to answer these questions. Now, I would also like to acknowledge the contributions from a number of people: Austin Boyd from Schlumberger, Mark Proth from Halliburton. I also want to thank Baker Hughes, Schlumberger, and Halliburton for allowing me to use some of their material with their permission to improve this presentation. I thank all of them. And with that said, I want to complete part 3 of the Carbonate trilogy. I hope you like the lectures. I hope you learn a lot. Please send me comments, questions, and until later, we are going for a more exciting, even more exciting topic on formation evaluation, to try to estimate storage, transfer properties of unconventional formations. How about that? I also plan to do a visit to the core facility to do an exercise of core log integration, and I plan to shoot a video about that and present the findings. I hope you're finding these lectures useful and informative. They're introductory, but yet they give you a sample of the problem. With that said, thank you so much, and hook and horns.